we made like a cool fractal paper thing, which looks like this. Yes, this is what we did yesterday. This is a Sierpinski triangle made out of paper. So today we're going to talk about mass point geometry, which is probably one of the hardest topics. So you guys should buckle in, but I hope that by the end of class, you will understand mass point geometry a little better. So, okay. So, okay, first, what do you guys know about like, oh, oops, okay. What do you guys already know about triangles? Like you can just put it in the chat, like what you know about them, everything you've got. Yes, they've got 3 sides, 3 vertices. They can have 1 right angle. The angles have to add up to 180 degrees. Yes, it is a polygon. That's what triangles and squares and pentagons are all polygons. Yes, Pythagoras did a lot of stuff with triangles. He came up with the Pythagorean theorem, which basically says like in a right triangle, the square of the sum of the 2 legs equals the square of the hypotenuse. Yeah, and there's different types of triangles. You have like acute triangles, obtuse triangles. Yeah. Okay, so you guys seem to know a bit about triangles. There's 3 sides, angles add up to 180. Area is 1/2 times the base times height. And also the triangle inequality theorem is something that tells us what the side lengths need to be in order to be a triangle. So the sum of any 2 sides in a triangle has to be greater than the 3rd side. Okay. Angela, you want to talk about this slide?
Oh, okay. Okay, so there's a special type of line which is called a Cevian, and basically a Cevian is any line that goes from one vertex of the triangle to the opposite side. So an example would be like the height of a triangle, like that could also be a Cevian.
Yeah, all of these lines shown here are Cevians because you can see they connect to one of the vertices and then touch the other side. And there's different types of Cevians. So there's 3 types of Cevians, and the type of Cevian basically is based on how you like make it. So for example, if you draw a line that connects from the vertex of the triangle to the midpoint of the other side, this is called a median because it's like connecting to the middle of the other side. And then like Angela just said, like the altitude of the triangle, which is also its height, is a line that goes from the vertex and is perpendicular to the other side. So it meets at a 90-degree angle. And then finally, the bisector of a triangle is a Cevian that basically divides the vertex angle in half. So you can see here that this line is dividing like this angle here into 2 equal parts, and that is called a bisector. Okay, so now we have a little bit of knowledge about triangles and what are Cevians. So now we're going to just completely switch topics to something else that is probably not like actually like pure math. We're going to do some physics. And as this picture shows, we're going to be doing some physics with seesaws. So the thing is, like, when you, let's say like you have like a seesaw, right? And you want it to be balanced. And so let's see, I don't have any props. Okay, we'll just use the picture. So in order for a seesaw to be balanced, you have to look at 2 things on both sides of the seesaw. You need to look at how much the object is weighing on each side. So in this case, you can see here, there's like 15 pounds and 10 pounds. And you also need to look at the distance the object is away from the middle, the center thing, which is called the fulcrum. So in this case, the left side is like weight is 2 feet away, and the right side weight is 3 feet away. And so in order to determine if a seesaw is balanced or not, the mass, which is the weight over here and over there, times the distance on each side has to equal each other. So yeah, Advika, it's like m1 d1 times m2 d2. They have to be equal. So basically the mass, so in this picture, it would be 15 pounds. The left side would be 15 pounds times 2 feet. So that's 30. And the right side would be 10 pounds times 3 feet. And that is also 30. And since these products are the same, then the seesaw is balanced. If they aren't the same, then it's not balanced. And it would be tilted to one side, depending on which one is bigger. Mass times distance, yeah, basically. Mass times m1, yeah, basically mass times distance on both sides has to be the same. So we can do a couple of problems with this. So for this seesaw, is this seesaw balanced? Yeah, this seesaw would be balanced because on over here, you can see it's 25 pounds times 4 feet, and that's 100. And on the other side, it's 10 pounds times 10 feet, which is also 100. And since they're equal, that means they're balanced. Oh, and also one more thing. So what would be the total weight that's sitting on the fulcrum? I know you saw the answer, but so what would be the total weight that's sitting on the fulcrum here? Yeah. So for this one, you just add up the weights on both sides. So you add up this 25-pound weight plus the 10-pound weight, and that would be 35 pounds. Okay, Angela, you want to do this next one?
Okay, so, okay.
Yeah. So this one would not be balanced because the left side has 8 pounds and it's a distance of 4 feet from the fulcrum. And the right side, it's 6 pounds and it's a distance of 6 feet from the fulcrum. So 32 does not equal 36, so this wouldn't be balanced. Okay, what about this one? Yeah, this one would be balanced because the left side is 12 pounds times 2 feet, which is 24. And the right side is 6 feet times 4 pounds, which is also 24. So what would be the total mass on the fulcrum? Yeah, it would be 16. And here's another thing, another important thing. If like a seesaw isn't balanced, you can't add up the things on each side to find the total mass on the fulcrum, because if it's not balanced, then one side is touching the ground. So actually the amount of weight on the fulcrum doesn't equal the total weight that's like sitting on the seesaw. So you can only like find like the total weight sitting on the fulcrum when it's balanced. Okay, one more. So is this one balanced? Yep, you guys got it. So the left side is 9 pounds times 4 feet, which is 36. And the left side is 4 feet times 12 pounds, which is 48. So those aren't equal, so this is not balanced. Okay. So you guys know how, right now we've talked a little bit about Cevians and triangle, and we've talked a little bit about how seesaw is balanced. So now we're gonna actually figure out like what mass point geometry is. So basically mass point geometry is a way to solve problems that involve intersecting Cevians in a triangle. So like if a triangle looks like this, like if the triangle looks like this, or if it looks like this, then you can probably use math point geometry to solve. And so that's why we talked about Cevians. And the way you use math point geometry is like you pretend like the Cevians and the sides of the triangle are all seesaws and they're all like connected to each other. And for each vertex, you assign the vertex a mass, just like you did with the seesaw. There was like a weight on each side of the seesaw. That's what you're pretending the points are. Those are the weights. And the line segments between them are like the distance to the fulcrum. So I can draw an example here. So we've got this triangle, we've got a line, we've got two Cevians. So in math point geometry, these vertices would have like weights on them. And these would be like the ends of the seesaw. And then you could look at any one of these line segments and you could just consider this whole thing a seesaw. So these are the weights. This is the fulcrum of the seesaw. And these and the lines on each side over here and over here, these are the distances. And then you just treat it like a seesaw problem and do that balancing thing where you assume it's balanced and then you solve for the unknown variable that way. And so the fulcrum of like a seesaw in like a math point geometry problem is typically where like the Cevian like intersects like a line segment. So it's an intersection. And so the whole time you're just using that seesaw thing. You guys clearly know how to solve seesaw problems. So you should be pretty good at math point geometry. So we can do a couple of smaller practice problems before we actually get into like the full size math point geometry problem. So here we can do some bird's eye view problems. So pretend like this diagram over here is a seesaw. It's just like you're looking at it from the top down now. So over here, like point A is the weight, point B is the weight, and point C is like the fulcrum in the middle. So we're solving for this question mark here. So yeah, you don't have to read all the text. You can probably tell from the diagram. So we are solving for the length of BC, which is also like just that distance. Yeah, you guys seem to have gotten it really fast. So for this, we sort of, I guess you could set up an equation, but it's not really that hard. So the weight at A is 5 and the length of AC is 4. So this side over here would be 5 times 4, which is 20. And then for the side up top here, it would be the weight at B, which is 2, times our unknown, which I'm just going to call X. So it's basically just 5 times 4 equals 2 times X. And so X would just have to be 10.
Okay, so for example 2, point A has a mass of 6, the length of AC is 2, and BC has a length of 3. What is the mass of point B? Okay, so I'm seeing a lot of correct answers. So 6 times 2 is 12, right? And 3 times the mass of B should also equal that. So 12 divided by 4. So the answer would be 4.
So how do they figure out the mass for like point A and point B? Like, do they just give it a random number, or is there actually a method to finding that?
We will go over that once we get into the real problems. But basically, they will give you a number and you can use that number. So yeah, they'll give you a number to work with. Yeah. Okay, another example. So for this one, it's a little different because there's 2 unknowns. So for this one, we're not looking for one specific answer, just what are some possible lengths for A, C, and BC? Yeah, so it looks like a lot of people are putting different answers and most of them seem to work. So remember that it's just, once again, it's just like a multiplication problem. 5 times AC equals 6 times BC, which I'm just going to call Y. So for AC and BC, we could have a lot of different things. So for AC, we could have 6, and for BC, we could have 5. For AC, we could also have any multiple of 6 and 5. So we can actually have AC be 12, BC be 10. We could have AC be, I don't know, 60 and BC be 50. It really doesn't matter. As long as it's a multiple of 6 or 5, it works. And in fact, you could also go the other way around. You could have AC be 1/5 and BC be 1/6, because that still balances out, right? It's just a different value. So basically, there's a lot of times where there's like when you're doing these problems, you'll find that it's really open-ended. You can choose basically any value that works. And as long as the only thing is that each of these, notice how like each of our values for AC and BC, even though you can have different values, they all have the same ratio. So the ratio of AC to BC is always 6 to 5, 12 to 10, which is the same, which is 6 to 5, 1/5 to 1/6, which is also 6 to 5. So the ratio of the side lengths and the ratio of the masses will stay the same, even though you can choose different values for it. So that will become really important when you come to real mass point geometry problems. Okay, and one important thing I kind of want to point out is that right now, all you've been seeing in these problems is just like a single line segment. Normally, you can't use mass point geometry on a single line segment. You can only use it when you have a triangle with intersecting Cevians. And it's just the reason why we like use it on a single line segment for the past 3 problems was just to get you guys like get the hang of like doing that seesaw thing.
Okay, so in real life, you'll have steps you need to follow. So again, you can only use this for triangles. So you label everything you know on the triangle by assuming the given values are the actual side lengths. And then you choose a starting seesaw and use that to solve for mass points and new distances. And you keep assigning mass points and new distances as you go around the triangle, solving for as much info as you can until you can solve for what the question is asking for. So that might not make sense to a lot of you, so we have an example.
So this might be something this would be like a diagram that you might see in a real mass point geometry problem. So if you just take a look at this triangle first, right now you can see that this triangle actually has 3 Cevians. They all intersect at one point in the middle, which is point G. And so because there are triangles with intersecting Cevians, then you know that you can use mass point geometry on this problem. So this is the question. The ratio of AF, so that's this line segment here, to BF is 2 to 3. And the ratio of BD, which is this one here, to DC is 7 to 2. So, and then it's asking, what is the ratio of AE to EC? So basically, it gives you like the ratio of 2 of the sides, and it's asking you for the ratio of the third side, but it doesn't even tell you any like actual like concrete numbers. It doesn't tell you the actual length of AF or BF. It just tells you like the ratio of them. However, as you guys saw in one of our last problems, we saw that as long as in a mass point geometry problem, you can like assign like any number to any side as long as the ratio stays the same. So for this problem, we can just assume the ratio is the actual side length. Like we don't need to like question what the actual side length could be. Let's just like assume the ratio is the actual side length. So it says the ratio of AF to BF is 2 to 3. So let's actually just say AF is 2 and BF is 3. Like that's perfectly fine. So we're just going to do that for all the numbers they've given us. We're going to assume they're the actual thing. So AF is going to be 2, BF is going to be 3, and we're going to label it on our diagram here. And then we're going to assume BD is 7 and DC is 2. And we're going to also label it on our diagram here. So now we've basically written down all the things we know about this diagram so far. So now the next step in our problem was that we need to like choose a starting seesaw and find the mass values around it. So you can choose any starting seesaw, but for this problem, I'm just going to choose AB as our seesaw, and we're just going to ignore the rest of the diagram. Like that's just going to disappear for now. So now we have our starting seesaw. So let's just solve for everything around it. So since you guys know how to do seesaw physics, let's just use that right now. And let's solve for the mass of A and B. So what are some possible values for the masses of A and B, where F is the fulcrum? Yeah, you guys put a bunch of possible values in the chat. And we're going to actually choose the easiest value to work with, which is going to be the smallest value. So I'm going to just say that A is going to be 3 and B is going to be 2 because that's the smallest value. And we don't want to do more calculations than we really need to. So we're going to do that and we're going to label it. And now we have our mass values, we have our distances, and we're going to go back to the full diagram now. Because once we have the mass values at A and B, we can solve for other mass values, such as the one at C, which would get us closer to this side, which is the side we're actually solving for. So what would be the mass value at C? Yeah, so the mass value at C would be 7. And we know this because right now, we're just looking at this seesaw down here, the BC seesaw. And so on the left side, we have the mass of B is 2 and the distance is 7. So 2 times 7 equals, and then the distance DC is 2 times the mass at C. So therefore the mass of C has to be 7. So we have the mass at C now, and we label it on our diagram. And so now we actually have enough information to solve for AE and EC. So what are some possible values for AE and EC? Yeah, so obviously there's lots of possible values for AE and EC. You could say AE is 7 and EC is 3. You could say AE is 14 and EC is 6. But either way, the ratio is always going to be the same. And so the ratio of AE to EC is always going to be 7 to 3. And that's the answer. Okay, are there any questions before we move on? Is anyone lost? Okay, that's good. Okay, I think we're gonna do a quick debrief and then we'll do one more example. So, yeah.
Yeah, okay. So takeaway so far is that if the question doesn't tell you the side lengths, then just assume the ratio is the actual length, and any starting mass value will work. And when we use our bird's eye view seesaw physics, we choose the starting seesaw, focus on that, and then we solve our way around the triangle. And the ratio of the sides will always be the same, even if the actual value may be different.
Okay. Oh, do you want to do this one, Shani?
Yeah, okay. So example 2, the ratio of AF to BF is 2 to 3, and the ratio of BD to DC is 7 to 2. What is the ratio of AG to DG? So we have the same triangle and a different problem. So we assume the ratio is equal to the actual side length, and we label the sides. So as you can see, we have already labeled the sides. So we can also reuse the mass values which we solved for earlier, because as we said earlier, that ratio 7 to 3 will always apply for this triangle specifically. So now we have these. So what equation should we set up for AG and DG? Remember that AG and DG are on this middle line. Here.
As a seesaw.
Yeah.
Like think about like the mass and the distance. So what mass is being multiplied by what distance, and set up an equation using that. Ooh, it looks like some of you guys are jumping ahead already.
Remember, right now we might not have all the values, so just put like the point or the line segment that would be multiplied together. Okay, I see a lot of you all getting the right answer for D. For the mass of D, it is 9. So the equation, but also we need to know the equation we would use, which would be AG multiplied by the mass of A, which is equal to DG times the mass of D. And we can rearrange this because we do need to solve for D. And yeah, okay, sorry. Because we do need to find the ratio of AG to DG. So we have AG divided by DG is equal to the mass of D divided by the mass of A. And we need to know the values of the mass of A and the mass of D in order to figure out what the answer is going to be. So we already know that A is the mass of A is 3, right? And you all said that the mass of D is 9, which is correct. So now we have 9 divided by 3, which will be our answer. So the ratio of AG to DG is 3 or 3 to 1. Yeah. Good job, everyone.
Yeah. And in case you didn't catch it, just an important thing to note is that because how we got D was because D is the fulcrum of this seesaw down here. So this seesaw here, D is the fulcrum, which means that the mass of D would just be the sum of the masses of B and C, because those are the weights on the seesaw. Okay, so now we're going to give you guys a couple of problems. We're going to see if you guys can solve them from start to finish. So this problem here, so the ratio of AE to BE is 2 to 5, and the ratio of BD to DC is 1 to 2. So what is the ratio of AF to FD? And we've already labeled like the ratio lengths on this diagram here. And we're just gonna probably just give you guys like a couple minutes and see if you guys can solve this through and through. And also, if you do have a piece of paper in front of you, I would recommend drawing out the diagram, because for this, you're going to be labeling stuff, so it might be helpful to draw stuff out. Okay, it looks like you guys originally had like a lot of answers that were 5 to 3, and then it got changed to 3 to 5. So let's see how we would do it. So first, what I would do is I would choose a starting seesaw, and I would choose AB just because we started with AB last time. And so I could just assign A a mass of 5 and B a mass of 2. That way the seesaw is balanced. And then we can solve for the mass of C. And that would be, we would give C a mass of 1 because 1 times 2 would be 2 times 1. And once we have that, we can solve for the mass of D because D is a fulcrum, which means that it's just the sum of B and C. So that would be 3. And once we have that, we can figure out a possible length for AF and FD. So AF could be 3 and FD could be 5. That would be the easiest values to work with, in my opinion. So the ratio of AF to DF would be 3 to 5. And I think you guys got a little confused at first because you were probably thinking, oh, like this vertex A is 5 and the vertex D is 3. So the ratio of AF to FD is 5 to 3. But it's actually the reverse because it's multiplied. So the value of 3 here would sort of be matched to this side, and the 5 up there would be matched to this side. So it'd be reversed. Okay, but it looks like you guys got that pretty good. So, okay, here's another one. This is not exactly a full triangle, but you still can use mass point geometry because there are intersecting Cevians. And in case you didn't know, this is a triangle. It's just the side here is, oops, the side here is missing. So that's why it looks weird. And the question is the ratio. Oh, wait, Ishani, you can do this. Sorry.
Okay, so the ratio of AF to BF is 1 to 2, and the ratio of BC to DC is 3 to 2. What is the ratio of AE to EC? So we have already labeled the sides with the ratios. So see if you can solve. Okay, so I am seeing some mixed answers, right? Some of you are saying 5 to 2, some of you are saying 5 to 4. So first let's just draw this line just so we can see that it's a triangle. And then let's just assign a value to B, right? So let's say B has a mass of 2, okay? And then let's say, and because of that, that would mean the mass of D would be 3 because 3 times 2 is 6. So we want 2 multiplied by the mass of D to also be 6, right? And then the mass of A, right, because we have the mass of B, that and 2 times 2 is 4. Then the mass of A will be 4 because 2 times 2 divided by 1 is 4. So that means the mass of A is 4. And then remember, C is the fulcrum of side DB. So that means that we have to add 3 and 2 together in order to get the value, the mass of C. So we get 5 here, right? So now, because we want to find the ratio of AE to EC, we need to find like lengths. So let's say CE is 4, then that would mean EA is 5, right? So that means that the ratio of AE to EC is 5 to 4. So that would be our answer. So for you all who got 5 to 2, perhaps when you put b as 2, you forgot that 2 times, like you forgot that 2 times 2 should equal whatever 1 times the mass of A should equal, and you just put 2 there, or on the flip side, you put B as 1, and then you got A as 2, and then you added 3 and 2 together rather than getting the mass of D and adding that to the mass of B. So you got 5 for this vertex, and you got 2 for this vertex. So remember that you're adding the masses of the vertices and not the lengths together when you are solving for the fulcrum mass. So yeah, keep that in mind.
Okay, so another few tips. So basically, if you think like a problem, like if you just like encounter like on a test or in a competition, if you think a problem might use math point geometry, but if you're just not really sure how to like go about solving it, I would just say like you can just start by like filling in as much information around like the diagram as possible, because eventually you just might up ending, you like if you're trying to solve for something but you don't know how to solve for it, just getting as much information as possible by filling in the math point geometry stuff, that can like lead you closer to the information you need. And the other thing is that once again, I think I already said this, but if a triangle has intersecting Cevians, you will most likely be able to use math point geometry. It may not be the correct approach, but it might be one of the approaches you try. So we have apparently made really good progress. So now we're actually going to look at some real problems. These are going to be harder than the problems we've encountered because they don't just use math point geometry. They do involve other things like calculating triangle areas and other ratios and stuff. But I think you guys got this, and I would like to see you give it a try. So Ishan, you can do this one.
Okay, so in triangle ABC, point D divides AC so that AD equals, AD to DC is equal to 1 to 2. Let E be the midpoint of BD, and let F be the point of intersection of line BC and line AE. Given the area of the triangle ABC is 360, what is the area of the triangle EBF? So, okay. Wait, should I walk them through it or should I give them?
Let's just give everyone a few minutes to just simmer through the problem. And if you need a hint, like if you want a hint, you can ask for a hint in the chat. And do keep in mind that because this is a math point geometry lesson, you will probably be using math point geometry in this problem, even though it's asking for you to solve for the area of a triangle, which doesn't seem to do much with math point geometry, but just work it out as much as possible. And once you're stuck, you can just ask us for a hint. Do you guys want more time or do you want a hint? Time. Okay, maybe I'll give you guys like another minute and then we'll give a hint. Okay.
Okay.
Shauna, you want to get?
Yeah. Yeah. Okay. So remember if you have like okay, I'll just draw an example triangle here. Right? So if I have like okay, if the ratio of like this is like the length of this is 2, okay, no, that's not a good triangle. But okay, let me okay. So if the length of so say for example, the ratio of this to this is 2 to 1. Remember, well, not remember, but that would also mean that the altitude would have a ratio of 2 here to 1 here. Simply because if you think about it, when you're okay, I don't know if you all know about similarity, but if you take a triangle and then you get a similar triangle, right, the ratios would be the same. So this smaller triangle would be similar to this bigger triangle. But anyways, that would mean that this would be 1, okay, and this would have a ratio of 1 to 2. So the altitudes would have the same ratio as these lines together. I hope that made sense.
I think another way to think about it would be like if you have like a triangle like this and you have like, I don't know, let's just say that's the height. So if you have a smaller triangle, right? Remember that the area of a triangle is 1/2 times base times height. So if the height of a triangle, so if a triangle's base is like, let's say it's another smaller triangle whose base is like 1/3 of the base of the big triangle, and whose height is like 1/2 the height of the big triangle, then the smaller triangle's area is going to be a fraction of the big triangle. That sort of like depends on the ratio, cough cough ratio, of the base and the height. I don't know if that helps or not, but I think me and Nishani are trying to say the same thing. Okay, Alex, we're doing math point geometry. Were you here for like the beginning of the lesson? Oh, okay. You could probably watch the recording, or you could have like your classmates help you. How about in the chat? Advika's already taking the lead. You can. Yeah, we do have a recording because I think you missed all of the lessons, so you can watch the recording. Okay. Wait. Okay. Just an update on the problem. Did that hint help at all, or are you guys still a little bit confused? Okay. Ishani, maybe we can walk through the mass point geometry part of the problem and give them a hint there.
Okay, so let's say that this vertex, okay, so let's start with vertex C, right? You can start with any of them, honestly, I believe, except for like F. So you can, so say that the mass of C is 1, right? Then 1 times 2 should equal 1 times the mass of A. So that means the mass of A is 2, right? And because D is the fulcrum, that means that its mass is 2 plus 1, since those are the masses of the vertices. So that's 3. Okay, I don't know if y'all can see this color, so I'll change the color. So if 3 is the mass of D, then 3 times 1 has to equal 1 times the mass of B. So that means that the mass of B is also equal to 3, right? So that means the mass of E is equal to 3 plus 3, which is 6. And the mass of F would equal 3 plus 1, which is equal to 4. Yeah, so that's the mass point geometry part of it.
Wait, you need to label the side lengths.
Oh wait, yeah, it's fine. Okay. So if this were 1, then that would mean that this would be equal to, okay, wait, hold on. Okay. My mind is blinking for some reason.
I can do.
Oh wait,
if you want.
no. Wait, so this would be 4, this would be 2, right? And this would be 1, and this would be 3.
Yes.
And
now we have all the information we need.
Yeah. So remember what I said or about like if this is 1-to-1, that means that the altitude, right?
Oh, Shani, I think you overcomplicated it.
Okay, yeah. Never mind.
I mean, it's the same thing. It's just that there's just more straightforward way.
Mhm.
Okay, wait. So if you think about, okay, remember guys said the area of a triangle is 1/2 base times height, right? So what is the base of the big triangle? Like, it's not the actual length of the base, but like the ratio length. Yeah, it's 4. So we're just gonna write 4. And what's like the one of the, it's not like, we don't actually know the height of the triangle, but there's a line segment right here, and we're just going to pretend that's the height. And I'll explain why in a second. So this, what is the ratio length of that? Yeah, 6. Now this does not actually equal 360. Let me just say that. That's not at the actual length of the triangle. We don't know the actual length of the triangle. And I don't know if you can even solve for the actual length, but we don't need to know the actual length because we want to look for like this tiny triangle here, right? So what is the base length of the tiny triangle? Yeah, it's 1. So let's write 1. And then what's the height? Again, it's not actually the height, but yeah, the height is 2. And now why can we call like this thing the height? It's because it's not the actual height, but the ratio of the height of this triangle to the big triangle is the same as the ratio of this side here, because I'm going to go back a little bit. Oopsie, why is it doing that? The ratio, okay, okay, let's use a different color. Here's the red. So this is like the actual height, right? This red line I just drew is the actual height. The ratio of this height here of the big height of the whole triangle to the little height of the little triangle is 6, is like 6:2. So the ratio of the areas then would just be this fraction, 1/2 times 4 times 6 divided by 1/2 times 1 times 2. So that ratio of the area is what's it called? 12, which means that the little triangle is 12 times smaller than the big triangle ABC. And the big triangle ABC is 360. And if the little triangle is 12 times smaller, then 360 divided by 12 is 30. So that would be the answer. So you see how like, I guess like at first you might not know how to use math point geometry to solve for areas, but the fact that math point geometry is about ratios means that it's very useful, because if once you know this one, you can just find the ratio for the little one. Yeah. Okay, are there any other questions about this problem? Okay. But yes, and one other thing I'd like to point out is that there are like multiple ways to solve this problem. Like you could have taken a Shawnee's route as well and done something slightly more complicated, but it would have gotten you to the same answer. And if you just look up solutions for this problem, there's like a gazillion solutions, and math point geometry is just one of them. So in my opinion, it's the easiest solution, but you know. Okay. This one is from an AMC 10, so it's from a harder test, and it's also number 20, so it's also a hard problem. So this problem is a little bit different. Well, hey, you guys got pretty close for the first one. So it's just I don't even think this problem is hard. It's just there's a trick in it. There's a trick. So you just have to be really careful. So okay, in triangle ABC, points D and E. So here, points D and E lie on BC and AD. And if AD and BE intersect at T, so that the ratio of AT to DT is 3, and BT to ET is 4, then what is CD to BD? And in fact, actually, I'm going to like, okay, wait, give me a second. I'm going to delete these. Oh shoot, oops. Oops. Well, you guys just saw the answer, but you hopefully didn't see the solution. So okay, you can work with those numbers, but do not feel obligated to like use them all the time. Sorry about that. Dang, okay, pretend like these numbers aren't here. You can label them with whatever number you want them to be. Like you can script, like if you don't want to use the numbers 4 and 1, because it doesn't tell you like the ratio is 3 to 1, it just tells you the ratio is 3. So in reality, you can use whatever number you want here, and that's my hint, because yeah, you guys should still, but since you guys all saw the answer, you have to explain how you got your answer, because I accidentally showed it to all of you guys. It has to be a mathematical explanation. Is anyone stuck? Would somebody like a hint? And if you get a different answer than the answer I showed, you should put the answer down because that teaches a really good lesson. If you guys get an answer that is different from the one I put down, then you need to type it in because if you don't put the answer down, then I'm gonna just solve it the wrong way and show you guys. Okay, looks like people are asking for some hints. So how far have you gotten in the math point geometry stuff? Like, have you gotten like the lengths of all the sides? Or and the weights and stuff. Yeah, so that's the thing. That's the trick with this problem. You get some of the weights, but then they're not balanced. So I'm gonna actually walk through the first few steps just to show you guys visually. So it says here BT over ET is 4-1. So like if I were just starting this problem, I would put BT is 4 and ET was 1 because that's like the easy way to go, right? And then AT is 3 and DT is 1, right? So that's all fun and games and everything. And then you probably go here and you're like, okay, B can be 1, E can be 4, and then D is 3, A is 1. And then you're like, okay, we need CD over BD, CD over BD, right? So we can like put like C is here or something like that. But that doesn't work because it's not balanced. And in fact, if you look at point T here, point T is definitely not balanced because the weights of, because T is like the intersection of two seesaws, right? And the weight of B up here plus the weight of E up here down here is supposed to equal T, which would be 5, but the horizontal weights add up to 4. So actually in this problem, the weights aren't really balancing. And so to solve this, we're just going to take a few steps back. We're going to, so if the weights aren't balancing in a problem like this, what you do is that instead of using like, notice how we started with like the weights of 4 and 1 and like 3 and 1, you can really start with any multiple of that. And if you want them to balance, then you want the distance of BT and TE to be the sum of that has to be the same as the distance from AT to DT, because otherwise the weights won't balance. So the sum of this distance has to be a multiple of 5, right? Because in the smallest possible, this value I've just put here was like 4 and 1. And so we could have like 8 and 2 as well. We could have, I don't know, 12 and 3 as distances, but the sum of the distances of BT and T always has to be a multiple of 5. And then the sum of the distances of AT and TD always has to be a multiple of 4. So because you can see here we have 3, 1. So we could have 6, 2, which is a multiple, 6 plus 2 is 8, which is a multiple of 4. We could have 9, 3, 9 plus 3 is 12, which is a multiple of 4. So we need to make sure these sums are equal. In order to do that, we need to find the least common multiple of that and upgrade it to that number. So like for BE, basically we want the sum of these distances to be a multiple of 4 and 5, and the sums have to be equal. So for BE, if we multiply the numbers we currently have by 4, and I'm going to erase the rest of my stuff because I'm going to clear. Okay, so if we multiply this by 4, then we'll get over here we'll get BT equals 16, and down here we'll get TE equals 4. And then if we multiply AT and TD by 5, we'll get 15 for AT and 5 for TD. And now if you notice these distances, BT plus TE, the total distance is 20. And over here, the total distance is 20 as well. And what that means is that then the weights will be equal. So now we can say the weight of like B can probably be like wait, could probably be like 1 now. And down here it can be 4. And for AD, the weight over here can be 1 and the weight over here can be 3. So now, oh wait, that still doesn't work.
Remember that you can have weights of like fractions, everyone. So like, and also if you can make the weight greater. So for example, the weight of B could be equal to 4 and the weight of E could be equal to 16. And this would work as a scenario.
There we go. So you basically find the least common multiple. If they don't match, you find the least common multiple of like the weights and you get them to be the sum up to the same number, because now both sides are summing up to 20, which balances the middle, which means that the side over here can be balanced, because notice how 5 plus 11 is now 16 and 11 plus 4 is now 15. So BD over here would be, you can assign that to be 11, and DC down here you can assign to be 4. So the ratio of CD to BD would be 4 to 11. Okay, does anyone have questions? Because I know this one was probably very hard. Okay, you guys don't need to worry too much about this problem because this is pretty hard. This is an AMC 10B problem, so. And it's also a problem that's near the end of the test. So, okay, I think we can probably just close this off with a easy Kahoot that does not involve like actual math point geometry problems. Oh, yes, we will be doing a Kahoot. I think all of you guys, hopefully. You can probably do a Kahoot on iPad. And we will probably give participation points for doing the Kahoots because, you know, Kahoots are fun. I don't think you're going to be able to see the questions on the screen. Let me see. Oh wait, yeah, I can do that. Okay, got it. There. That's probably better. Okay. If anyone else wants to join, you should do it soon. Somebody left. Okay, you're back. Okay, let's begin. Okay, math point geometry. Okay, question 1. The blank is the line that connects the vertex of the triangle to the opposite side. Yes. That was someone chose celery. Okay, cetacean. Okay, most of you guys got it. It's a Cevian. Noel is in first place. First place is in second place. That's ironic. A line that splits an angle in half is called a yeah. Yes, it's called a bisector. And frusty yummy is basically, I was thinking of a frustum because I was thinking of random math terms. And then a frustum sounded too like boring, so I added yummy at the end. Oh, Advika's in first place. First place is still in second place. What is a median? Okay, so I'm not sure how you would. Okay, a median is a line that cuts the opposite side in half. I'm not sure about a line that divides a triangle into two unequal sides. That's not really the definition of a median, even though I guess it kind of does that. Okay. Oh, first place is in first place now. How far must the 4-pound weight be placed in the fulcrum to keep balance? And by the way, that symbol is a pound symbol, not 16. Yes, so most of you guys got it. It is 10 feet.
I'm 8 points behind you, Brian.
Sriram is in first. What is the name of the method we just learned today? Oh, good. All of you guys got it right. If you didn't get it right, it would be a little sad.
Yes, coin probably.
Okay, Sriram is still in first place. The ratio 1 to 4 is not equivalent to. I mean, we did a lot of stuff with ratios today. Okay, this one, all those zeros in the back don't matter. Like, you can ignore those. This one is equal to 2/5. Sriram is still in first. When might you use math point geometry?
When there are circles, of course.
Yeah, yes, when there are intersecting Cevians. Okay, using our seesaw analogy, the points on a triangle are assigned. Yes, you assign the points and vertices with weights. Okay, using our seesaw analogy, the lines are assigned. Yeah, the lines are assigned the distances.
They are assigned a job to help us with the correct answer.
Doesn't matter what the starting mass of a point is. Yeah, so for this one, it doesn't really matter what the starting mass is. You can change it later if you really want to. You just preferably choose the easiest mass, but honestly, you could assign whatever mass to it you want. It's just all the masses of the points that follow do matter, but the first mass does not matter. Okay, what is the mass at point B?
$39. That should have been an answer.
It should have. But yes, it is 16 because you just add the weights. Okay, can you use math point geometry on a line segment that doesn't intersect any other lines? Okay, so you guys got tripped up by this. So this is an example of the yellow option, which it looks like most of you guys chose. So this is a Cevian, although the problem is a Cevian does intersect other lines. So it can't be a Cevian unless it intersects lines, you know, because the Cevian has to touch the other side of the triangle and the vertex. So a Cevian by definition touches other lines, which is basically intersecting other lines. So really, if a line like it's just isolated in the middle of math world or something, in the middle of a math plane or something, you can't really do a whole lot with it, and you can't really use math point geometry on it. Oh, oops, I skipped past it.
There better be a wrong answer to this.
Oh, there's no wrong answer. Okay, so it looks like some people said no, a couple people said yes, some people said a little bit, and then some people said, what do you mean hard? I don't know what do you mean hard means, but I'm assuming that means not hard. So, okay. In third place, we have Sriram with 12 out of 13. In second place, we have Samvi with a full score. And in first place, we have first place.
Who was first place?
First place, review yourself. Look at who's smiling the most, and then perhaps they will be maybe they are the first place person. No, it's not me. Okay, now the person is trying very hard not to smile.
Who could it be?